All right. Thank you, Steve, and I want to also thank the other organizers for the invitation to this workshop, and also thank you all for sticking around and coming to my talk. So I'm going to be switching gears a little bit. I'm going to be talking about a method called kernel analog forecasting and applying it to multiscale dynamical systems or data generated by multiscale dynamical systems. And this is ongoing work with my collaborators, Andrew Stewart at Caltech and Dimitri Giannakis at NYU Courant. So we're going to be using some ideas from kernel methods, reproducing kernel Hilbert spaces and Koopman operator theory in this talk. So machine learning for dynamical systems is a challenge because machine learning maps a finite set of input data to a finite set of response data. And the challenges for forecasting data from dynamical systems are that sometimes you only partially observe the dynamics, and therefore you lose Markovianity in your observations. And when you predict, when you construct a predictor using learning methods, you also want a way to enforce the dynamical structure and ensure consistency in the limit as you collect more and more data from the system, and also get an estimate of uncertainty outside a training window. So an application of this would be, for example, climate, where you obviously don't have access to the underlying state space, which is the entire ocean in this case, but you want to predict oceanic Niño index, which is this average measure of the deviation from a certain threshold of the temperature over this region. And this has implications in global climate and climate change and things like that. So here you see a plot of the Niño index over several decades. And suppose that you train on this data, you would not only like to get a prediction outside this training set that is physically consistent, and also you would like an estimate of the uncertainty when you construct this predictor. And our approach will be an established method called kernel analog forecasting, which was developed by my collaborators, Dimitri Giannakis. So the setting we're working with is an ergodic, possibly nonlinear flow, which is denoted by the state space omega that we cannot access. And we denote the flow map on these dynamics by phi t. And we assume there's an invariant probability measure mu on this state space omega. We also assume a continuous observation map x, where we collect data points xi, which can be vector valued. And we assume a scalar valued response variable of interest, zi, which is the output of this response map that we assume to be square integrable over the L2 space of the system, of the dynamics. So we have these time-ordered pairs of training data, and we would like to construct a predictor function, z tau, that predicts our response variable over a user-specified lead time tau. And this is the basic idea of our method. So given a new snapshot of a satellite sea surface temperature data that can be vector valued, we would like to forecast the response variable or Niño index associated with that new data tau time steps ahead. And one of the initial inspirations for the method that we are proposing is a naive approach called analog forecasting, originally proposed by Lorenz. And the idea is to take the new data that you have and look at the data in your training set that is closest to that new data point in some metric, and take the associated response variable in your training data and shift it by the number of time steps you want to get your prediction. And clearly, one of the drawbacks of this is that it depends discontinuously on the xi. And we assume that we have a continuous observation map X, so we would like a continuous predictor that's physical in this sense. So instead of optimizing to a finite set of training data, which is what we're ultimately doing in the end, we would like to optimize over a space of functions. So our true predictor is F, our response mapping composed with the flow map. This is our perfect forecast. And we would like to optimize over some as of yet unspecified space of functions that map from the observation data to your desired predictor, shifted tau time steps ahead. And we can also rewrite this forecast, F composed with the flow map, which is our true prediction, in terms of the Koopman operator. So the Koopman operator in this, given our assumptions, is simply F composed with the flow map, and it shifts your observable, your response variable, which we will also call an observable, tau time steps ahead, without ever observing the underlying state that generated it. So this is a useful concept because although we have an unknown nonlinear flow map in state space, by lifting to this function space, we have a linear operator acting on the response in L2 that we can use to define our idea of what the prediction should be. So here we just rewrite the objective as this. So we want to construct a predictor, as I said before, in a Hilbert subspace of L2, which I'm calling Hx, which denotes the set of square integrable functions acting on the observation data. So it's a subspace of what F can be, for instance. And the minimal predictor in Hx, in the L2 sense, is given by the conditional expectation. So this quantity captures a notion of information loss when you only observe partial dynamics. And it's essentially a projection of the Koopman time-shifted observable onto this Hilbert subspace. So as of yet, I've kept this space of functions abstract, but now we're going to specify that H, the space we're optimizing over, lies in a reproducing kernel Hilbert space. And these have certain beneficial properties, including that every symmetric positive definite kernel or kernel function corresponds to an RKHS uniquely and vice versa. And this is the famous Moore-Aranjan theorem. So given a kernel acting on our observation data xi, xj, for each xi and xj, you have a kernel function value associated with it. And G here can be represented by an n by n matrix where we have n training samples. And pointwise evaluation is provided by the kernel function. So essentially, evaluating a function at a new data point would correspond to an inner product with the kernel section evaluated at that data point. Just to summarize, we would like to construct a predictor in this space, but we would like to construct it in the span of these kernel eigenfunctions. So suppose we have L of these kernel eigenfunctions, we would like to construct a predictor in this finite dimensional subspace of this RKHS. And I will tell you how on the next slide. And essentially our predictor is an expansion in terms of these kernel eigenfunctions evaluated at a new point, the kernel eigenfunction expansion coefficients, and the eigenvalues of this kernel matrix, which I'll tell you how to construct. So the practical consequences of building this in an RKHS is that due to the properties of the kernel function, the kernel matrix that we construct from it is an approximation to an integral operator that acts on the sample data via an n by n kernel matrix. And the eigenvectors only take values at the sampled data xi. So we can represent these spaces L2 of mu by these vectors, n-dimensional vectors. Because remember, we only have a finite amount of training data. We want to map these finite dimensional eigenvectors to the eigenfunctions that we can evaluate pointwise. And the kernel is the means to do that. And this is the crucial utility of an RKHS in our setting, the pointwise evaluation of the forecast UTF that I had on the previous slide. So G that I showed you before on the previous slide is a matrix composed of these pairwise kernel entries. And it also represents an integral operator that is the composition of this extension operator and a restriction operator. And this extension operator maps elements in L2 here to our finite dimensional subspace of the RKHS. And the way we do this is using this pointwise evaluation property, which is also known as the reproducing kernel property. So we compute psi j by taking the eigenvectors of this kernel matrix, which we have already computed, and evaluating the kernel cross-section with these eigenvectors at our observed data point. And this gives us a pointwise evaluation of psi j at x. And these values, these psi j correspond to the RKHS basis functions. So the utility of the RKHS is that it gives you an explicit way of mapping from finite dimensional kernel eigenvectors, which only take values at our sample data, to out of sample data. And using a calculation on the projection of our Koopman operator, we can approximate them from the time-shifted responses. So here, we are taking the inner product of phi j evaluated at the observation data and UTF, which is given in our training data by time-shifted values of the response variable. So this is how we're approximating the action of our Koopman operator on our training data. And now we can construct our forecast at lead time tau, which is assumed to be an integer multiple of our sampling time interval, to get our forecast. So there is a consistency result proven by my collaborators in the large data limit. So when n goes to infinity, which is where n is the number of training samples, this predictor composed of the observations converges to the conditional expectation of the true forecast, or what we have defined as the true forecast. And it's this iterated limit. So first you take the limit as you have infinite data, and then you take infinitely many eigenfunctions. So we're going to apply this methodology to multiscale systems with clear timescale separation between slow and fast variables. And we're going to only observe the slow variables, which are often approximately Markovian for certain classes of multiscale systems. So here we have our x, which is coupled with our fast variables y, and y is the y dynamics are scaled by this epsilon parameter, which defines our timescale parameter. So as epsilon goes to 0, y will become, y and x will be, their scale separation will increase. And in these regimes, depending on whether you notice homogenization or averaging in the multiscale system you're looking at, the conditional expectation simplifies, and we have a notion of what we are supposed to see in the forecast. And I have two examples of one of each. In addition to the forecast, you can also have a notion of uncertainty in the forecast by taking the RKHS extension of the error between your forecast and your true trajectory. So instead of taking the time-shifted value of your response as your observable, you instead take this error between your actual predictor and the true trajectory on your training data, and then you use the same procedure as before to extend it and compute the new coefficients here, and then you can plot error bars with each value of your forecast. So our choice of kernel for these examples is the variable bandwidth radial basis function kernels, which account for large variations in the sampling data. And these have some data-dependent parameters that you have to tune, but there are automatic tuning parameters that are summarized in these papers. So you have this bandwidth parameter that you have to tune anyway for the radial basis function kernel. And you also have these estimates, kernel density estimates of the sampling density, as well as an estimate of the manifold dimension of the observed submanifold, if there is one. You do this normalization procedure to make sure the rows and columns of this kernel matrix sum to 1, and also ensures that you have a symmetric, strictly positive definite kernel that satisfies your assumptions before. And then you compute the SVD of this intermediate kernel matrix to get your kernel eigenvectors. So you don't have to construct G explicitly. And this kernel becomes relevant for our next example, which does have variations in sampling data and a non-compact manifold. So here you have a slow variable, which is forced by the fast Lorenz 63 dynamics. So these are just the Lorenz 63 dynamics, and you have a forcing from the Lorenz 63 dynamics here. And we're taking epsilon very small, and that means that the y dynamics are 2 orders of magnitude faster than the x dynamics. And it's a result by Givon, Kupferman, and Stewart that as epsilon goes to 0, the slow dynamics x of t provably has an SDE limit driven by Brownian motion. So this is an example of homogenization in the dynamics. So you see here that x is a potential flow forced by Brownian motion. And we know a lot about this system and can compute the conditional expectation explicitly, which gives us a nice verification of our results. So our observable is only the x variable, and we are forecasting based on the x observations only, not the y observations. So here you can see the trajectory we are training on. And here you can see the probability density, the histogram of this trajectory, and you can see how closely it fits the invariant probability density of this stochastic process that we know a lot about. We can explicitly compute its invariant measure. So here is a long-term forecast of the conditional expectation. We know that the conditional expectation should converge to 0, just looking at the density function here. So this is the mean, and we know it eventually converges to 0, but it should do so in a continuous way. So we can see that as we increase tau and compute many, many predictions, we can see that our forecast, which is in blue, depends continuously on x, and it converges to the true conditional expectation plotted by this black line, which is computed by 10,000 realizations of this SDE initialized at x naught equals -1. And we can also see that the uncertainty estimates that we get closely follow the trajectory and saturate where the trajectory has its extrema. And here is a look at a shorter time window. This is the conditional variance of the error. You can see that you have a smaller uncertainty when you start at -1, which is one of the lobes of our attractor, and higher uncertainty when you start at 0. The system spends very little time at this point, it's going to switch to either 1 or -1. And you can see that the method adaptively expands to accommodate the trajectory. And here's the side-by-side comparison, just so you can see how the method adapts. So these are the kernel eigenvectors that we have computed, the first 7 or so. So here are the kernel eigenvectors, and we know what they should converge to for this particular system. They are dependent on the geometry of the manifold, the eigenfunctions of the G matrix we compute converge in the infinite data limit to the Laplace-Bertrami heat operator of the limiting SDE of the stochastic process. And these are the actual eigenfunctions analytically evaluated. And you can see very close agreement between the two, which explains why we get such a good forecast. The drawback with this system is that the trajectory does not really inform you about the conditional expectation, or the other way around. And so now we're looking at a regime where this trajectory or the conditional expectation should closely approximate the true trajectory, which is more relevant in a lot of applications. So here we look at the multiscale Lorenz 96 system, which is much higher dimensional. It has networked chaotic multiscale dynamics with the slow variables coupled to the fast ergodic variables. So here we have 9 of these slow variables, xk, and they depend on their corresponding 8 fast variables explicitly, and they have these periodic boundary conditions that are not on this slide. We collect data from the slow variables only, so the first 9 xk variables, and we want to predict them at the macroscopic timescale in the future. And as epsilon goes to 0, the y dynamics are averaged out, and the xk approximately behave deterministically on each other. So the xk variables behave approximately Markovian, and this system exhibits averaging for ergodic y. So as epsilon becomes small, this average right here starts to look more and more like a function that depends only on the other x variables. And that's because as epsilon becomes small, you can hold the x variable fixed while you simulate the y variable. And the density of the y variables depends on a fixed x. And these are averaged out by that sum you saw by this expression here, and simplify to depending on the other x variables. So in this case, the conditional expectation disappears, and you should see that the trajectory and the forecast should track closely and are approximately deterministic. So here we have 2 different trajectories, one of the x1 variable and one of the x7 variable. And you can see that the predictor actually does not just converge to the middle like the previous system. It actually tracks the trajectory because the conditional expectation should disappear as epsilon becomes small. And here we're taking epsilon is 0.001 or so. And you can see that for short term, this predictor closely, it's actually right on top of the trajectory, but that you do see this damping effect in both trajectories. But also the uncertainty actually follows the trajectory closely and actually stays in phase with the Lorenz dynamics, which is pretty remarkable given that we have already surpassed the Lyapunov timescales at tau equals 2. So beyond this, it's unreasonable to get a good prediction without observing more data. And that's because this system is chaotic to the initial conditions, or sensitive to the initial conditions. And so to conclude, we have a lot more ideas for what to do with this kind of methodology, including generalizing our choice of observables and observations to perhaps delay embeddings and seeing if this damping effect goes away. And one of the reasons we see this damping effect is because we're projecting onto a finite dimensional subspace of the Koopman operator. And another contribution of this effect is that the conditional expectation should eventually converge to 0 for mixing dynamical systems such as this one. And we can see closure of the slow variables for certain classes of multiscale dynamics. And this may be useful where you have clear separation in certain climate phenomena or molecular dynamics. And I'm excited to see if anyone has any data where you can apply this. And some open questions are how to generalize to a vector valued response variable. Instead of stacking a bunch of observables and forecasting them independently, what if you have a single vector valued observable where the components depend on each other? And that's an open research direction. So I'll leave it at that and open the floor for questions.